Very welcome. Nice to see a few new faces again today. So we'll get the ball rolling with Aline Melo. She's going to be talking about geology and overlap between geology and medicine and some insights from that perspective. I'll let her explain that in more detail. The only thing I'll highlight is seed funding call from Una Europa that Katrina is happy to help out with. So there's lots of other events coming up, but I'll hand over to Aline from School of Geology and an Ad Astra fellow in UCD since 2020. So getting well established at this point, so I'll hand over.
Thank you. Yeah, so thank you guys for having me here today. So Will told me, and from the previous conference I've been to, is a very, very diverse audience. So I try to really focus on the main ideas, lots of images. Feel free to ask any questions you might have. So yeah, I'm not going to talk a lot about geology or medicine, so mostly on geophysics. But that's a good analogy to try to understand what geophysics is. And basically, when you have a stomach pain and you go to the doctor, will the doctor just cut you open and try to find a problem? Hopefully not. We say no. No. So what usually happens? They ask for exams, right? Yeah, maybe not best way to start a talk, but yeah, I think it's interesting to think that when we want to know more about the subsurface, so what's below our feet, we can't cut huge holes everywhere for kilometers down to try to figure out what the problem is. So we don't want to be this type of doctor with the earth, right? In the same way, we need to know more about the human body and where the source of the pain or anything happening, any problem happening is, like with the earth. If we want to know more about the subsurface, we can't just open holes everywhere. We need to find ways of getting information from down there without damaging or spending billions and billions, right? So example of a pregnant person. So if you want to know if the baby is well, again, you don't cut the bump open and, hey, baby. So we do an ultrasound. So basically, what's an ultrasound? What's the physics behind an ultrasound? So if you have a womb and a baby happy there, very, very, I think it's the most happy time of anyone's life, because though I actually know the world where you're coming to. But anyway, when you're very happy there, best time of your life ever. So you go to an appointment and there is a sensor for the ultrasound. So very cold or sometimes warm gel on you, just to make sure there is no air. And then you put the sensor. And the sensor has a transmitter. This transmitter is going to create sound waves, the same waves that I'm creating when I'm talking to you. They go through the air, touch the membranes in your ears, and this vibration is converted into words, and your brain processes everything I'm talking to you. Same physics. So it's a transmitter sending waves, and these waves, very specific frequencies, are gonna reach the baby. So it's not advised to do many scans, because this is actually disturbing. It's like someone screaming at you while you're there, happy, right? Just enjoying the liquid, I guess. Anyway, so these waves are gonna go through the baby, and we know tissue, skin, bone, liquids, everything has a different property, different structure. So the waves, when they touch different parts of our body, they will reflect back and will be captured by a receiver. And when they reflect back, they are going to change amplitude and intensity, depending if you're reaching bones or liquid. So that's why we can make an image like this one: black part, liquid, white part, bones, high density, high acoustic impedance. So it's going to be be giving a very high amplitude reflection. So that's how we can make an image, right? So that's the physics behind. So when I was pregnant, every time I was going to go to a scan, I was super excited. I was like, yes. And my husband, yeah, don't you want to know if she has 5 fingers? Oh, yeah. So anyway, I was very nerdy. I don't think the doctors really enjoyed all my questions, but anyway, it's really cool to see the same physics we do on Earth, right? We do have a transmitter and sensors, receivers. So we do create these same waves, different frequency, different amplitude. This is an example what we call like a seismo vibro size. It's a big truck just boom, 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 creating a lot of noise. Waves travel depending if the rock dense has more clay, sand, more it's like foliated, or is just isotropic. This all will have influence on the reflections in the same way that bone or liquids or whatever in our bodies. And then we capture the amplitude and the frequency of these waves back. These are the geophones, and we can do this on land or water as well. And that's how we can image the subsurface on the same way we do image our bodies. So we can create images of the subsurface very, very similar to scans. And in this example, we can know, okay, these layers are flat. Here we have a fold, we have a fault. And all this is important for us to know where water is going to be, or gas, petroleum. So this was used a lot to find petroleum resources. Now we are revisiting this data to try to find areas where we can trap CO2, for example. So how we can use the same technology to understand the subsurface, to make sure we also find the mineral deposits. Mineral deposits, they are very, very rare and unique occurrences that depend on a set of factors to happen, very like a tumor in a body. So when you look at images and you try to find anomalies, we also try to find these anomalies to find new mineral deposits, and lots of similarities in the technology. So here is just a quick example of a study in Southeast Brazil in an area that's now producing petroleum. And each dot, if we, again, draw this analogy with medicine, each dot there is a point, the green dots here, is a point of where we did a biopsy. So in the same way, when we look at those images, oops, I keep moving and changing. Sorry, my grandfather, he was Italian. So if you hold my hands, I can't talk. Basically, yeah. So anyway, in the same way you do in medicine, if you have an image of the body and you find something anomalous, you suspect it could be a cancer or a tumor or something. Before surgery, we usually do like a biopsy. You go with a very thin needle, collect a little bit of the sample and do an analysis. We do the same in geoscience. So we do the biopsy with what we call drill holes or wells. We do sample the earth with a drilling rig, which is a very big machine, and go sometimes to 5-6 kilometers. 100 meters, and we can go to many kilometers, and we take samples to analyze. So this is an area where one of my master's students analyzed this type of ultrasounds or images of the earth, and we could define the thickness of the salt layer, find where there is a higher probability of finding petroleum, and where the best areas are for CO2 sequestration to make sure you can inject and keep CO2 there. And we apply all sorts of techniques to calculate what we call the seismic attributes, to find very specific information about changes in amplitude and density, to help us differentiate between different layers and try to come up with models or hypotheses for what the composition of all these layers are. And in this same case here, when we want to know about what's going on the subsurface, we do what we call a cross-section. It's basically same as slicing a cake and looking at the subsurface, what's in there. And we can derive those 3D images of the subsurface. In this case, we use sections of these images to try to know where are the shallow and deep areas. And each black line represents one of these points where we did a biopsy, where we have samples. The challenging part is that for the human body, we know how the organs look like. In earth sciences, we not always know how the rocks look like and all the variations there. So actually, what these two fields don't have in common. So one of the things is that we don't always know what the geometry of the things we're looking for are. And the other things that, for example, if you do magnetic resonance imaging, this machine, I don't know if anyone has done, very, very uncomfortable and loud. So it's not possible to sleep. Like I know people, I slept for an hour there. It's like, oh, maybe your snore is higher like than the noise of the machine. But anyway, it's like a 360 thing. You can image the whole body in 360. When we talk about the Earth, it's obviously very big. So this is only Ireland in green, of course. So if we want to do a geophysics survey, a very large one, we might do half of the country, will take months and a lot of money. So we are not lucky, like in medicine, to do this 360 images with the sensors very, very close to the body. Basically, let's say I want to know how a brain looks like, and I put one sensor right here to do one measurement. And I want to know the shape of the brain. Very, very challenging. But that's how it is. That's life. That's what geophysicists have to do. And in Ireland, we're very lucky. We have this TALUS program from the Geological Survey Ireland. This is the equivalent of a MRI of Ireland. So we have this image showing the response of the magnetic rocks. So we can tell where rocks are more magnetic. Northern Ireland is definitely very different from the rest. We can derive some structures related to dikes, faults. We can see big trends related to the tectonic past of how Ireland was formed. But one difference is that in a magnetic resonance image, you can see slices through the body. Here, unfortunately, it's like you take out the slice, sum up, and create one image, because we don't have sensors all over the planet. So, and then we end up with this image with frequencies from different depths, and we need to operate a miracle to see a 3D thing to actually know more about the subsurface. And that's a big question. And we apply inversion theory from mathematics, which is adapted to geophysics, to create images of the geometry of the bodies at depth. So this inverse problem in science is this process of calculating from a set of observations, our data, what's actually causing this data to be like this. We are basically trying to mathematize, I don't know if this exists, probably not, but we have this geology, which is so fascinating, like looking at a mountain, and then we need to find equations to explain this. Very difficult, but still we try anyway. So yeah, the geology, the mineral deposits, the shiny stuff. So gold, copper for electricity, metals for your phones, everything we do, we need for having a comfortable modern life come from rocks. everything comes from the rocks. So all the metals, not wood, of course, but all the metals and things come from this shiny material. In this case, it's called chalcopyrite. And they have physical properties like bone is different from tissue, from liquid. They have different densities, susceptibilities, conductivities. And these changes in physical properties change the fields around us. And the physical fields is what we try to measure. And we have all the equations from Newton's equation in the case of density and the gravity field of a geological body to Maxwell's equations in case of susceptibility, conductivity. Of course, we don't have time for the math, but all the equations connect the fields we measure with the properties we want to know. So we use these equations to actually do the opposite. We measure the data, we try to model the properties so we can do some interpretations, derive some ideas about the geology using the same equations. So I've set up a lab here to measure these physical properties. For example, this is a lab for biopsy without blood. I don't like blood. That's why I went to geology. Rocks don't talk, don't bleed, don't complain. If you throw them on the ground, they will be there and you can just do nothing about it. So rocks are great. But lots of students and people, and and then life gets complicated. But anyway, that's the fun part, teaching. And so we have a lot of machines to try to do this biopsy, to try to actually look at the rocks and actually understand what their properties are, so we can derive better underground subsurface images. Quick example, Limerick region. We have sedimentary cover everywhere. And this is a problem for me. This is actually great for Sam and Clara. That's why they study the cover. That's the beauty of life. People look at different things. So if we look at the different geophysical images and the rocks, we measure the properties of the rocks. We try to understand how they vary and try to connect with the geophysical data. You see, this is a geological map. It's what's supposed to look below the overburden cover. But those are the only points we actually know what the rock actually is. So a lot of uncertainty on this, a lot of interpretation. So we are trying to use all these images to create, all this data to create 3D images. Here in pink, we see the volcanic rocks. So there was a volcano in Limerick about 300,000 years ago, which is really cool, right? Not only in Limerick, but one of the regions. And how does these rocks look below? Is this deep, shallow, one center, multiple centers? And this is the work of one of my PhD students trying to image these volcanic centers to see like, okay, it looks like we had two main magma conduits. This one is pretty shallow. It's probably going from one of the main conduits. And knowing all this helps with, okay, what's the potential for geothermal? Because usually these areas still have a lot of heat from the past. So geothermal energy. Mineral deposits. We know a lot of mineral deposits. Like here, there is one called Stone Park, and here there's another one called Paula's Green. A lot of zinc and lead in these deposits, and we do need zinc and lead for infrastructure for constructing wind turbines. So Mark here from School of Earth Science as well, he does a lot of research on wind, but if we don't find enough metals, you won't have ways of actually putting a wind turbine to create energy there. So yeah, and why all this is important? Decarbonization. So to construct infrastructure to decarbonize, we need a lot of metals. Here are the metals for solar panels, wind turbines, or electric vehicles. We need so much metal. It's expected that in 2040, we will need 4 times more than what we use now. It's a huge amount of metals. And all these metals are in rocks. So we do need to find more metals in a responsible way. So, and how actually we should be doing this? Discovering more primary metals. That's the main part of my work. Sustainable discovery. We need to apply technologies that have low footprint, low impact. As I told before, we can just make huge holes and see what's down there. So geophysics is part of this low impact set of techniques. So we do examine things first, and increase and improve recycling. So phone doesn't work anymore, it's thrown away. How much of that is actually recycled? And we do need to spend a lot of investments on this. And yeah, that's all I had for today. Thank you. If you have any questions, let me know.